So, welcome back. In this lecture again we discuss the question of extension of a function to a larger domain and some density results. So, we have already seen some extension results and density results for some special domains, namely rectangular, parallelepiped and cubes. Okay. So, we are going to use those results and obtain an extension result for a general domain. For that we need to put some conditions on the boundary. So, I will first start my discussion with a general definition of surfaces and integration over the surfaces. Okay. This is a brief introduction that is sufficient for our purpose. Okay. So, let me start with a discussion on n dimensional surfaces in Rn. Okay. So, we also call them hypersurfaces. Okay. So, let me start with a simple thing. So, let S1 be a simple piece. That is, so this is a special case of a surface, that is S1 is described by an equation of the form Vx prime. So, this I have chosen these coordinates for simplicity, but this could be any. So, this is in Rn. Okay. So, this S is one sitting here and you project it to Rn minus 1, and that is the domain, that is the surface Xn, the n dimensional hyperplane Xn equal to 0, and so this X prime is sitting somewhere here. So, this is, I call it D, this is in Xn equal to 0, and any point here is denoted by X prime, and so a point in S1 is nothing but X in Rn, where this nth coordinate is given by phi x prime for some x prime in D. Okay. Such a thing we call it a simple piece. Okay. So, on such a simple piece we can immediately, so this, for example, if you want to compare it to, so this any surface need not be a simple piece all the time. So, in 2 dimension you can get some examples. Okay. So, this is, I will write as just x and y. Okay. So, if you take a curve of this type, you can only project it onto x y equal to 0, but if you take something like this, you can always project it to onto x equal to 0, but then in between you can always, so there are many curves, either we can project onto maybe some other color just for the illustration. So blue. So if you have curve like that, so you can project either onto x equal to 0 or y equal to 0. Okay, so these are some, but then there are also complicated curves, so which are not simple. Okay, so this you can have like that. Okay, these are not simple. Okay. So we can, similar to the line integral in R2, we can define the surface integral on a simple surface, integral on S1. So if f from S1 closer, so S1 itself we can assume it to be closed, but okay, I'll just write it is continuous, then its integral, so I'll write it integral over S f ds. This is by definition. So you can again use, for example, Riemann sums and etc. So you can easily see this one. So this is f x prime p x prime, and then there is a factor, this 1 plus grad phi square. Okay. So this is dx1 prime, I'll put. So this is an n minus 1 dimensional integral. And remember, this D is the projection S1. Okay, let's put S1. Projection of the simple piece S1 onto this hyperplane xn equal to 0. Remember that. And this grad phi square, so we are going to use, so here phi is function of n minus 1 variables, so grad phi square. So I will not explicitly write every time, the variables may be different. So in this case I will just write, so just remember this and compare this with your line integral. Okay, so this is just an extension of that. So in this discussion on integration on surfaces, we always deal with functions which are functions of n minus 1 variables, and this grad phi square is with respect to those n minus 1 variables. They may not be all the time x1, x2, xn minus 1, but one variable missing from x1, x2, xn. Okay. So for our purposes, we consider, okay, just I forgot to mention one important thing here, this phi. So we need some smoothness. So phi is Cm. Okay, so and m is at least 1. Okay, then we call this simple piece of class Cm. Okay. So now we extend this one for other surfaces, and we consider surfaces. So, n minus 1 dimensional surfaces S which are finite union. Okay, so for our purposes it's finite union of simple pieces. Sj. Okay, so this means S is Sj, say j equal to 1 to n, and each Sj is a simple piece. And if each Sj is of class Cm, so again M is at least 1, then we say S is also of class Cm. Okay. So, let us write in elaborately what Sj is. So, Sj, okay, Sj is given by, so now let me write xp some coordinate, and this one is phi j. So, x1, x2, xp minus 1 and xp plus 1 xn. So, this coordinate p depends on j. Okay. There could be more choices as we saw in R2, and so this is projection onto xp equal to 0, and that domain you call it dj. Okay. So, this is consists of all the points x1, xp minus 1, xp plus 1, xn. Okay. And phi j is from dj to r, and the points of Sj are given by x1, x2, xp minus 1, and pth coordinate is replaced by this function phi j, and rest again the variables are same. Okay. So, in this case when I take grad phi j square, it will be with respect to these variables. So, just remember that. Okay. So, there could be again some overlapping here because we are not assuming disjoint union. So, we need to be little careful in defining the integral. Okay. So, again let f from S closer to R be a continuous function. So, for a simple piece we have defined the integral of f over S, and now we extend that. So, define in fact using again Riemann sums, actually you can get this integral. Okay. So, just for our purposes I am just defining this f ds. Okay. So, now this S contains, S is union of n simple pieces, but there could be overlapping, so we have to take care of that. Okay. So just n integral, I will say dj prime. Okay. So prime, because we have to avoid the overlapping. Okay. So let me call it fj. So there is a function fj, I will define that, and then you that usual one, 1 plus grad phi j square. Okay. So this, let me write it once. It's cumbersome, but you have to remember. Okay. So again this is an n dimensional, n minus 1 dimensional integral. Okay. So the variable xp is missing there. Okay. So what is dj prime? So where, so you start the counting somewhere, so that you take it full. Okay. d1 prime is d1, and for j bigger than 1, so dj prime is the projection of, so we don't want sj, so we have to remove that overlapping. So projection of sj, the simple piece, minus, so you remove them. So I equal to 1 to j minus 1, and projection where, onto xp equal to 0. So remember, p depends on j, onto this hyperplane. Okay. In that way we avoid overlapping. Okay. And then we take the corresponding gradient square there. And what is this fj? And so fj is more generally defined on dj. So fj, let me repeat, x1 xp minus 1 xp plus 1 xn is equal to, let me, I have used superscript, so let me just continue with that, fj. So this is nothing but f of, so the variables remain same here, because f is defined on s closure, so we have to get a point on the s. So this is p minus 1 phi j of those variables, and rest of the variables same. Only the pth coordinate is replaced by phi j. Okay. And these are in, more generally in dj. So dj is the projection of sj onto the hyperplane xp equal to 0. Okay. And of course now we have to, the task is to verify that the definition is independent of the choice of the simple pieces. So whatever the given surface is union of those simple surfaces, this integral is independent of that. That's one thing one has to do. Okay. So that's left as an exercise. And this one, so let me just, is called ds is called surface measure on S. So it depends only on the surface we consider, not on the simple pieces that make up our surface measure on S. Okay. So this, of course, we are, just remember, we are doing it for continuous function. So here you can just use the Riemann integration, so there is no problem at all. Okay, so that's that is fine. Okay, and now we want to extend this notion to discontinuous functions. So in essence, we would like to develop a measure and integration theory on surfaces, and of course this is again a big topic. So I just recall here in a brief manner, starting from the notion of set of measure 0, there is a way we can develop measure and integration theory. If you have not seen it, so it's good time to see that. So you can build the entire Lebesgue measure and integration theory starting from Riemann integration and continuous function, and with the notion of just a set of measure 0. Okay, so we are going to just define the set of measure 0 in S, and that enables us to develop the whole measure and integration theory on surfaces. Okay. So set of measure zero in S. And this is just a primitive concept even for the Euclidean spaces. So the same thing we are going to use here. Okay, so if again Sj is a simple piece, Sj is a simple piece. So why we are using that? So we can project it onto some hyperplane. Simple piece. Let dj be its projection onto some hyperplane xp equal to 0. Okay, again remember this p depends on pj, and there could be more choices. Okay, but that doesn't matter. Okay, so we say a subset E in Sj is of surface measure 0 if, okay, so let me draw this diagram. So yes, j is sitting here and dj is sitting here. So this is the hyperplane xp equal to 0. Okay, so this is some E here. Okay, let me use different. So some piece. Okay, so there is a corresponding set here. So you call it E tilde. Okay, which is, this is under that mapping that defines, okay, there is a phi j here. Okay, so that's okay. So that via phi j you get that E tilde. Okay, if, okay, E tilde contained in dj, okay, which is pre-image of E under phi j. Okay, so just remember that. Okay, is of n minus 1 dimensional measure 0. So this is the usual Lebesgue measure on Rn minus 1, that is xp equal to 0, n dimensional measure is 0. Okay. So once we define this concept of set of measure 0 on a simple piece, so its extension to S is immediate. Okay. So a set, a subset E now in S, okay, which is again finite union of simple pieces, is called a set of surface measure 0 if E intersection Sj. Okay, so this is subset of simple piece Sj has surface measure 0 for all j 1 to n. So just remember, S is this union of Sj, and each Sj is a simple piece. So this notion of set of surface measure 0 helps us in defining two functions defined on S equal almost everywhere, and then you can define the measurability of a function, etc. So I will skip that thing, but you can develop that. So okay, so from here means the notion of set of surface measure 0, one can develop a theory of measure and integration on S starting with continuous functions. So in order to develop, so the even in abstract way, if you know integration on a specific class, for example here continuous functions, and the notion of set of measure 0, then you can develop a theory of measure and integration starting from continuous function. Okay, that is very interesting, and the same formula extends to the same formula. This is, so also star is also valid. So let me just write here. So star is also valid for measurable functions. So measurable functions are almost everywhere limits of continuous functions, sequence of continuous functions. Okay, so that whole theory there is also valid for measurable functions, and then you can also define what measurable functions are integrable functions defined on S. So in particular, we can talk of the space L to S. So similar to the L2 space on Euclidean spaces. So now with respect to surface measure, so these are class of all measurable functions defined on S, which are square integrable. Okay. So I'll just list a couple of references here. Okay. So this of course we have to leisurely sit and do all the computations. Okay. So just let me okay. Where is the two references? So where you can, so from here one can develop. Okay, let me just mention that one. Okay, further developments. So these are important developments, and you can also current literature you can find. So once we develop this measure and integration theory, so we can talk of distributions. Okay, first before that, let me just so integration theory on manifolds. Okay, so these manifolds are more general than surfaces. Okay, so once you develop integration theory, you can talk of distributions on manifolds. So you will find lots of literature on this, and then eventually you analysis of PDE on manifolds. So for example, over the sphere, torus, etc. Okay, so this just notion of integration on a surface leads to these developments. So in this context, I would like to say two references. Okay, so one is this Raghavan Narasimhan. Of course, these are bit old books, but still very relevant, and to learn something afresh. Analysis on real and complex manifolds. this is published North Holland. This is 1973. Okay, so in this book you find the development of integration on manifolds, and it also contains a chapter on PDE where some elliptic regularity are discussed, and there is a discussion on Sobolev spaces also. So you can look into that. Another one is Lars Harmander. These are not easy books, easy to read. So this Harmander has 4 volumes on this linear PDE. What I am referring here is volume 1, which is relevant for our course, and this exclusively deals with distribution theory and Fourier analysis. Okay, so this is Springer second edition. Okay, that's what I, maybe there is other edition now, but this is what I have. Okay. Okay, with mentioning of those 2 references, I stop here, and in the next class we use this notion of integration theory on and smoothness of the surfaces in order to obtain a general result on extension of functions. Thank you.